When an electrical fault occurs inside industrial switchgear, solid metal vaporizes in milliseconds. The resulting plasma cloud reaches temperatures exceeding 35,000 degrees Fahrenheit, nearly 4 times the surface temperature of the sun. Simultaneously, copper conductors expand to 67,000 times their original volume, generating a massive concussive pressure wave known as an arc blast. This chaotic explosion contrasts with the predictability of normal electrical distribution. Under standard operating conditions, power flows predictably, with current safely constrained by physical conductors and heavy insulation. Electricity behaves predictably when contained, but it converts into a destructive bomb the moment it bridges an air gap. To understand how facilities protect workers from these blasts, we need to deconstruct the physics of an arc flash and examine exactly how engineering studies predict where and when these events will happen. The safety protocols technicians follow daily, like those in the NFPA 70E standard, derive from rigorous mathematical models. To manage the lethal physics of an arc flash, professionals rely on deterministic engineering studies to map the exact limits of the hazard. Every industrial electrical safety plan begins by mapping the entire distribution network, tracing the path of power from the utility substation through pad-mounted transformers to the main switchgear and individual subpanels. During normal operation, the flow of current through this network is strictly dictated by the connected equipment, such as motor loads and lighting. Accurately modeling this baseline condition, mapping every conductor length, transformer impedance, and utility contribution, is the mandatory first step before analyzing what happens when systems fail. A fault occurs when that normal path is disrupted. If a technician drops a metal wrench across 2 live bus bars, it creates an unintended path for the current, bridging a phase-to-phase gap. This creates a bolted fault, a direct physical contact between conductors, where current flow is limited only by system impedance. An arcing fault is different. The short circuit travels through ionized air. This air gap acts as a resistor, significantly reducing the total current flow compared to a solid copper bolted fault. An arcing fault pulls less current than a bolted fault, and this specific behavior creates a deadly blind spot for standard electrical safety equipment. To measure the danger of that blind spot, engineers calculate incident energy. Incident energy is thermal energy measured at a specific distance. Because arcing faults pull lower current, they often fail to trigger instantaneous breaker trips. This delayed reaction time causes duration to scale up, which massively inflates the total energy released during the event. A delayed breaker trip allows the plasma cloud to burn longer, increasing the thermal radiation and pressure wave hitting anyone standing nearby. This incident energy calculation dictates the arc flash boundary. The arc flash boundary is the physical distance from equipment where incident energy drops to 1.2 calories per square centimeter, the threshold for second-degree burns. Lower current often translates to a longer, more lethal plasma burn because the slower reaction time of the safety devices allows energy to accumulate. Because incident energy is dictated by so many variables, engineers rely on the mathematical models provided by the IEEE 1584 standard. IEEE 1584 is the industry guide for performing arc flash hazard calculations. Specialized software builds a digital twin of the network, factoring in enclosure dimensions. This short-circuit analysis finds the maximum fault current at every node, identifying over-duty components, where the available energy exceeds a breaker's physical capacity to safely interrupt the circuit. An over-duty breaker can catastrophically fail and explode, rather than clearing a short circuit. These software models require precise field data, including exact conductor lengths and transformer impedance. Bad inputs yield dangerously inaccurate safety boundaries. The short circuit study forms the foundation for facility safety. Worker protection begins with mathematically proving that the equipment can survive the initial blast. Once the equipment is proven capable of handling the fault current, engineers perform the final step, adjusting how fast the breakers react to those calculated faults. Selective coordination ensures only the breaker closest to the fault trips. Time current curves, or TCCs, help engineers visualize this. By adjusting trip settings to shift these curves, engineers can reduce a 2-second clearing time to just 0.1 seconds, preventing lethal energy accumulation. Proper selective coordination is an essential tool against arc flash. By reducing clearing times, engineers minimize the total incident energy released during a fault. All of this abstract engineering software ultimately translates back to the physical reality of the switchgear on the facility floor. The final deliverable of that modeling is the data printed on an NFPA 70E arc flash hazard warning label. A technician reads this label to determine the exact level of arc-rated personal protective equipment, or PPE, required to survive a blast while working on that specific panel. PPE is the last line of defense. The true goal is to establish an electrically safe work condition. An electrically safe work condition is a state in which an electrical conductor or circuit part has been disconnected from energized parts, locked out or tagged out, and tested to verify the absence of voltage. Advanced physics and coordination studies are only effective when translated into strict lockout-tagout procedures and enforced human behavior. An arc flash is a chaotic and deadly physical event, but its parameters are mathematically predictable. By combining short-circuit analysis, coordination studies, and strict safety policies, facilities can manage the extreme physics of an electrical fault. Because electrical systems change when equipment is installed or utility inputs shift, these engineering studies require regular updates to maintain accurate safety margins. To learn more about electrical safety and hazard mitigation, subscribe to the HSE Study YouTube channel. Continuous education and rigorous engineering practices ensure every technician goes home safely.